This is part of the P2 topic, but it is for triple science students only. So it's all about infrared radiation, which you have come across some of the ideas about infrared before. So let's just do a recap. And this is actually of year 7 because it's related to the light topic that you did in year 7. So we should know that light is a spectrum. Okay, so what you did in year 7 was you learned that if we had white light and we split it up, that we would split it up into the colour spectrum, and that the colours of the colour spectrum are red, orange, yellow, green, blue, indigo and violet. Okay, so it splits it up into these, and this process we call it dispersion, so it's dispersed the light. We usually do it by putting the light through a prism. So that's what you should already know. So actually light is part of a wider spectrum, and this is called the electromagnetic spectrum. And you will no doubt have heard of some of these before anyway. So we have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. So some of these you will have heard of before. So microwaves are the same as the microwave you use at home to cook your food. Radio waves, again, you'll have heard of them in terms of the actual radio, and that's how the signal gets sent. Visible light, this is what we're talking about when we say visible light. And you might have heard of ultraviolet or UV in terms of the sun. X-rays, they are the X-rays that you would have if you had a broken bone. The rest, I mean, the whole electromagnetic spectrum you do about when you're in year 11. But for now, we're just talking about this part, infrared. Okay, so as we can see from this, and as the name suggests, visible light is the only bit, that we can actually see. Okay, and again, we could write out the colours of the colour spectrum here. Notice that we've got red at one end, and that will then go into infrared. We've got violet at the other end, and that then goes into ultraviolet. Okay, so it's this constant spectrum that goes from radio waves all the way to gamma rays. So infrared, we have to detect infrared. So I'm going to call it IR just because that's what we use when we mean infrared, and it just saves me writing out the whole thing. We can't see it. If we could see it, then it would be part of the visible spectrum, but we can't see it. Okay, so we could use a thermometer because it's detected as a temperature increase, as heat. So what we could do is we could get a prism and we could put in kind of light here, which is then going to split up like this. Okay, and then if we had a screen and we held a thermometer just here, then we would be able to see that there'd be a temperature increase there. If we moved it further away, we wouldn't be able to detect that temperature increase. But if we hold it just to the side of the red part, then we will be able to see that there's a temperature increase because that's the infrared that's increasing that. The other way, so that's a thermometer. The other way that we could do it is by using an infrared camera. So this is a special camera that picks up on the infrared radiation rather than the visible radiation. And you might have seen this being called a thermal imaging camera before. So what else do we know? we need to know that all objects emit infrared radiation. But the higher the temperature means that there is more infrared emitted. So emitted just means given out. If it is a constant temperature, then what that means is it is emitting at the same rate it absorbs. Okay, so emitting is to give out. Rate just means it'll be the same amount in a certain time, over a period of time. We then have something called black body radiation. So first of all, we need to know the definition of what a black body is, and this is something that absorbs all the radiation that hits it. So it doesn't reflect any, it doesn't transmit any, it absorbs all of the radiation. We should know from year 8, I think, when we did a bit about energy, that if something is a good absorber of radiation or of energy, then it's also going to be a good emitter. So it's going to absorb all the energy, the radiation that hits it, and then it's going to emit all the radiation from its body. Okay, so body just means object. So black bodies are the best emitters. So they're the best absorbers, they absorb all the radiation, and then they're also the best emitters. And the radiation that is emitted from a black body is called black body radiation. So you might have done an experiment in year 8 where you had test tubes or boiling tubes that were different colours, and they had hot water in them, and you measured the temperature change, and you would have found that matte black things absorbed and emitted radiation the most, so the temperature would have changed the most. Shiny silver things reflect a lot of the radiation, so they're not very good absorbers, and they're also not very good emitters. That's a term that you need to be able to use, and you need to know the definition of it. And then the last bit that we're just going to cover, if something is a constant temperature, so let's just take this over here, then it will emit a continuous range of wavelengths. So what do we mean by that? Well, we might need to remember that light is a wave, and that the wavelength changes across the spectrum. So over here is a longer wavelength, and then the wavelength gets shorter as we get to this end. It's not a very good diagram, but we've got a longer wavelength here. Remember that a wavelength is a whole oscillation, so it would be the distance from like a peak to a peak, that's a wavelength, and then here would be a wavelength as well. So at this end of the spectrum we have short wavelengths, at this end of the spectrum we have long wavelengths. Okay, so there's a continuous range of wavelengths for an object that is at a constant temperature, and the intensity is highest at a specific wavelength. And this specific wavelength that it's highest at is related to its temperature. So let's draw a graph so that we can see what that would look like. So if we had a graph of intensity against wavelength, okay, so it's going to emit a continuous range of wavelengths. Let's do that in that original colour. And it will have a peak at a specific wavelength. If we increase the temperature, then the intensity at all wavelengths increases. And the peak wavelength decreases. So what's that going to look like for our graph? Well, the intensity at all wavelengths increases. Let's think about that to start off with. So at all of these wavelengths, the line has to be higher than the purple line that we've drawn, because the intensity has to be higher at all points. But on top of that, our peak wavelength decreases. So where this dotted line is, has got to decrease. So our peak needs to be somewhere like here. So what will end up happening is something like this. Okay, so our peak wavelength has decreased and the intensity is higher at all points than the original graph. Now if you have a go at the questions, pause the video and then come back and have a look at the answers and see how you did. So draw an experimental setup which enables you to detect infrared radiation and explain how you can detect it. So we talked about this in the kind of explanation bit at the beginning, where we talked about there being a prism and having white light that is directed into it, and then that being split up into the colour spectrum, this being put on a screen, and then as having a thermometer there. This is a prism, white light. Okay, so that's the draw the setup, explain how we can detect it. A lamp's glowing filament emits radiation at a range of wavelengths at the same time. You see this mixture of wavelengths as one colour. Which colour of light has the longer wavelength, red or blue? Which type of electromagnetic radiation has the longer wavelength, visible light or infrared? A lamp's filament behaves like a black body. A black body's temperature can be judged by its colour. List these black body colours in order of lowest to highest temperature. A small block of metal is placed close to a filament lamp. The lamp is then switched on at high intensity. Initially, the metal block's temperature increases. Compare the block's rates of emission and absorption whilst its temperature is increasing. After a while, the metal block's temperature becomes constant. Compare the block's rates of emission and absorption while the temperature is constant. The lamp is switched off and the metal block cools. Compare the block's rates of emission and absorption while the temperature is dropping. Describe as fully as you can the energy transfers and processes which cause them when a lamp is on at constant brightness. When the lamp is on at constant brightness, the filament stays at a constant temperature, even though it is emitting radiation at a higher rate than it is absorbing radiation. Suggest why. We're talking about, so we've got a filament lamp, so that's a bulb that looks, like got one of those wires inside. So the wire heats up, gives out light, and then the whole thing lights up. Even though it's emitting lots of radiation and not absorbing very much, there's still an input of energy by the electric current. When you switch off a lamp, it quickly dims until it stops glowing. Explain this observation in terms of emission and absorption from the filament. So we already know from this that emission is at a higher rate than absorption, but now we've removed the power supply. So there's no more energy input. The graphs show the intensity or brightness of radiation versus wavelength for a black body at two different temperatures. So this is the graph that we sketched before. Describe two ways in which a black body's radiation changes according to the graphs when its temperature increases. So this line is 1000 degrees Celsius, this line is 750 degrees Celsius. So we can see on this one that the intensity is greater at all wavelengths. And we can also see that the peak intensity is a lower wavelength, shorter wavelength. A filament's temperature can get as high as 3000 degrees Celsius. A black body, which is even hotter than this, can look blue. Suggest why. As temperature increases, the wavelength gets shorter. So it's going to move from, so this is the longer wavelength, so this is the shorter wavelength. Okay, so it will move from reddish to orange, and then it will start to look blue. All objects emit and absorb infrared radiation. The hotter an object is, the more infrared radiation it emits in a given time. Black body radiation is radiation emitted by a body that absorbs all the radiation incident on it.